Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Good morning. This is lecture 14, which will cover relative motion analysis, part 3, where we will use all the techniques developed in the relative motion analysis to analyze 4-bar linkages mechanism. And we will look at one example in particular, which is a representative example of a 4-bar linkages. This is a 4-bar linkages. It's a special class of mechanism that can be used to achieve certain type of movement. If you look around, there are robotic arms that look like 4-bar linkages and special transportation lift which looks like 4-bar linkages. Even though what is seen is 3-bar linkages, e.g. what you can see is OA, AB and BC, the 4th bar is actually OC, and this is somewhat hidden, and this is considered as the 4th bar. In terms of construction of the 4-bar linkages, you will have the arm OA or the link OA, link AB and link BC, and there are pin joints or hinges, and which we assume to be frictionless. So if you start to move the arm OA, you will see that arm BC will also move together. So this is where you want to achieve a certain type of movement. You can control the length of arm OA and the length of arm BC, and you will find that you can achieve a certain type of motion using the movement of arm OA and B. For example, if I draw here, if I were to rotate OA for about 45 degrees, if I were to rotate OA 45 degrees, you can see that let's say it's about 45 degrees from there, so it's about here, and therefore BC will also follow suit, and you can find that this is the new position of the horizontal bar. So this is case where we move OA counterclockwise, and therefore BC will move in the same direction. So you can imagine certain mechanisms are moving in that way. Okay, so how do we analyze the 4-bar linkages? So you use the same technique as before. We identify the coordinate system and then look at the position vector, and from the position vector write the position vector equation, and from there you can derive the velocity and acceleration equation, and then you can also find here the fixed points. It's not A but O. Fixed points are O. O is fixed. This point is fixed O, and C is fixed, so that we know we can use that link OA is rotating about a fixed axis O, and link BC is rotating about a fixed axis C. So you can use that equation of rotation about fixed axis, which is the basis of all of our analysis, and then from there we identify the I and J components. These are the standard techniques that we use throughout this whole lecture or whole class in order for us to identify the output velocity of the link when we know what the input is. So let's see how we use this. So for example, when we look at the coordinate system, so let's draw our X and Y in that direction. So we know that's a common direction, and then from there you draw the position vector. So if I took OA as the position vector, and this is position vector B relative to A, so I can write that position vector B relative to A. This is position vector A. And what about this line? This line is the position vector B relative to O. So I can now write the equation of position vector B relative to O, and I know that O is not moving, so I can remove O. I can just write position vector B equals to position vector A relative to O. I know O is not moving, so I can write position vector A only, so I can remove O altogether. So I can write position vector A plus, which is this vector position vector B equals to position vector A plus position vector B relative to A. So I can write that position vector B relative to A. So from there, I can write the, done with my position vector. Now I am here. I need to write, I've already write down the position equation, position vector equation. I can now write down the velocity and acceleration equation. So the next task is to write down. So then we know VB equals to VA plus VB relative to A. And we know that AB equals to AA plus acceleration B relative to A. So you know what to look for. So then we identify the fixed points. What are the fixed points? The fixed points are point O and point C. Point O and point C are the fixed points. So for point O, point A is rotating about, so I can write down here that I use a different color, like link OA, link OA rotates about O. What about the other point is link BC rotates about C. Yeah, so link OA rotates about O, link BC rotates about C. So I wrote here my statement. Link OA rotates about O, link BC rotates about C. What are the equations that we can use for this? So we know that the relevant equation would be, what will be the relevant equation? So we know that VA equals to, because it's rotating about O, equivalent to omega OA cross position vector A relative to O. So what else? And we can use acceleration A because its rotation about fixed axis. You know, it's alpha OA cross position vector A relative to O. This is the tangential acceleration minus omega square OA position vector A relative to O. This is the tangential component, and this one is the normal component. So this is tangential, and this is the normal component. So what can you write about? Same thing you can use about B, point B. So we can write about, so I'm using the same technique here. So VB, let's do break here. VB equals to omega BC vector, position vector B relative to C, and then AB, about the vector AB, the same alpha BC cross position vector B relative to C, and then the normal acceleration is omega BC square minus omega BC square position vector B relative to C. So that I can now box these two equations. What else do we have? We missed anything? Yeah. Now we don't have is we now have VA. We have VA. We have VB, VA. What about VB relative to A? What about VB relative to A? So now we need to write our VB relative to A. So let's use a dark color. VB relative to A equals to omega AB cross position vector B relative to A. Yeah, so that's VB relative to A. What about A position acceleration B relative to A? It is the same formula. Yeah, so B relative to A. It's rotating about A, so is alpha AB cross position vector B relative to A minus omega square AB. Let's see this position vector B relative to A. Yeah, so that's the third box. Alright, so that, I hope you can follow how we develop these arguments based on the basis of the past 2 lectures. So by now you know the steps needed to solve equations related to 4 bar linkages, and basically we have the same equation recurring for all the links, as long as you know what the links are and how they are related in terms of position vector, acceleration, and velocity. So this is example 14.1 example where of 4 bar linkages. 4 bar linkages mechanism is shown below. For the instance shown, the link AB is horizontal and the angle AOC is 30 degrees and ABC is 45 degrees. If the link OA is rotating at angular speed of 4 radian per second counterclockwise and accelerating at 2 radian per second square, accelerating is positive according to the direction of the velocity, determine the following. The angular speed of link AB and BC, and the angular acceleration of link AB and BC. So in this case, the input is the link OA. We want to know what is the acceleration and the velocity of link AB and link BC. So let's read again the question of 4 bar linkages mechanism here. So the link AB is horizontal, so AB is horizontal, so parallel to OC, assuming, and the angle AOC is 30 degrees, so this one is 30 degrees. Let's draw that 30 degrees here. So this is 30 degrees, and the ABC is 45 degrees. This is 45 degrees. So this is parallel. This line is parallel. Yeah. So this angle is also 45 degrees. What else? So I just put here omega 4k, also 4 radian per second, and alpha equals to 2 radian per second square. And I set all the data that we have. So the first thing we do, is just we'll put our coordinate system. So here is our coordinate system, x and y. So that's coordinate system. What is the second thing we do is we draw the position vector. It helps me in my thinking. So this is my position vector A, okay, and this position vector B, okay, relative to A, underline, that's a vector, and this is position vector B relative to O. And because O is not moving, so I can now rub it off. So I just, and A was O, so A relative to O is not moving, so it becomes position vector A. So that's the position vector. So after that, I would write down the position vector equation. So I know the position vector equation is position vector B equals to position vector A plus position vector B relative to A. So with that, I can write down the velocity. It follows the same nomenclature. VB equals to VA plus velocity B relative to A. And it's also follow that we can write the acceleration equation. AB, acceleration B equals to position A plus acceleration of B relative to A. So that's the first steps. I have all the equations. Now I need to identify the fixed axis rotation. So let me highlight the fixed axis rotation in orange. So I know this is my pivot O and pivot C. So why is it important to me? So when I see a fixed axis rotation, I know that I write something right? Link, link OA and link BC are fixed axis rotation. Okay, that is important to me from the dynamic analysis because it will dictate what kind of motion. So therefore VB, because of its fixed axis rotation, equals to omega OA K, we assume, yeah, the direction, cross position vector A. And and then we have, what about VB? VB is omega BC K cross position vector B relative to C. Now I'm going to remove some of the signs here to give me some space. Okay. So sometimes student would ask me, why are you not using position vector B relative to O? So let's see that. So some of you might ask a big question like, why, position vector B relative to C. So I'm going to highlight this. So the question is, why not? Why aren't you using position vector B relative to O? Yeah. So that is a question. A big question. So let's box this question. The reason being is that VB, even though in the position vector we put position vector B, and therefore its associated is VB, and VB here is omega OA cross position vector. This is VA. This is VA equals omega A OA cross position vector A, and VB is omega BC cross position vector. Because why? Because the link OB doesn't exist. Yeah, there is no such things. So I'm going to highlight that in soft green so that you can remember that it doesn't exist. The link OB doesn't exist, and VB is the speed or the velocity of point B on link BC. See here, when I identify that point, my mind sees these points is a fixed axis rotation. Okay, I hope it will clarify to you why we don't use that. So let me finish the third question. The third equation is VB relative to A is, yeah, you guess it right, omega ABK cross position vector B relative to A. Okay, so these are the three sets of equations. Let me box this equation so that 1, 2, and 3. So in order to solve this omega, we need to find the position vector of each. So maybe we should use the different slides. So here is a position vector A. Position vector A is, we know this angle there. This angle is 30 degrees. AOC is 30 degrees. This is 45 degrees. So this angle is 45 degrees. Quickly. So position vector A relative to O is, position vector A is 0.4 cos 30 degrees I plus 0.4 sine 30 degrees J. Yeah. And then position vector B is 0.5 cos 45 degrees I plus 0.5 sine 45 degrees J. Yeah. And position vector B relative to A is very straightforward. It is, B is 0.8 to the right of A in the positive x direction to 0.8 I. So we know that VA equals to omega A B K cross position vector A. Yeah. But we know omega AB is 4 radian per second counterclockwise. So that's a 4K. So I'm going to take this off and put 4K. And I know that position vector A, I've calculated the position vector A above. So I'm going to take this off and I'm going to put the vector there. So it's 0.346I plus 0.2J. Okay, and that gives me, and I can also do that with VB. I don't know what VB is. I assume it's omega ABK cross, I know what position vector B is, 0.354I plus 0.354J. Yeah, and I know what VB relative to A is. It's omega AB. I'm not sure what. So this is VB, sorry, VB is omega BC. Oh, I make a mistake here. This is omega BC. This VBA is omega AB K cross, and B relative to A is 8I. Yeah, so you can solve this. So I've written here all the answer. So VA I've calculated 4K cross position vector A relative to O is 1.38J minus 0.8I. Yeah. So the other one is VB is omega BC cross position vector B relative to C, 0.35I, 0.35J is 0.354 omega ABJ minus 0.354 omega AB. I'm running out of space here. And then finally, VB relative to A is omega ABK. K cross I is minus J. So it's minus 8 omega ABJ. So when you put all the equations together, VB equals to VA. So remember that the equations, the big equation is VB equals to VA plus VB relative to A. So here's the big equation. Yeah. So I'm going to write it down here at this corner. So I know what VB is. VB is 0.354 omega AB J K cross I minus 0.354 omega ABI equals to VA. I know VA is 1.384J minus 0.8I plus VB relative to A minus 8 omega ABJ. I hope I've done all the calculations correctly. So if we take the I parts or the J parts, let's see what's the easiest one. So the I part would be the easier one. So let's say that if I take the I parts, then negative 0.3 0.354 omega AB equals to minus 0.8. So so then I get omega AB equals to so we can from this sets of equation we can find that omega AB is equals to 2.26 radian per second. First question, that is the first answer. And then when you look at the J parts, so if you look at the J parts, yeah, so 0.354 omega AB equals to here 1.384 J BV omega VBC VB equals to, oh, I've made a mistake here. Okay, hold on. I'm making a mistake here. There was a mistake before this, so I've changed again. VB equals to omega BCK cross this position vector, so we got 0.354 omega BCJ and then 3.5 omega BCI. So here when we put all those equations, omega BCJ, this is the VB, equals to VA plus VB relative to A. So here is a case of, and I take the I parts, and then I 0.354 minus 0.8, then omega BC is 0.8 divided by 0.354. I've got omega BC 2.26 K radian per second. So when I'll do the J parts, let me erase something here. So when I do the J parts, I'll erase this too. Yeah. So when I do the J parts, I'll use a different color. When I do the J parts, I'm looking at this component. Omega BCJ equals to 138 minus omega AB. So I'm going to rewrite that. So 0.354 omega BC equals to 1.384 minus 8 omega AB. Yeah, so we know omega BC is 2.26. So we said that omega AB equals to 0.354 times 2.26. 2.26 divided by 8. And then there's a minus sign here. So let me remove this a bit to the left. So it's a minus. So omega AB equals to minus. Yeah, so this 2.26. So I notice I made a mistake here. Position vector B relative to O is 0.8i, so I'm going to erase this. This is not 8i here. So I've transferred the equation before, VB equals to VA plus VB over A, and this is 0.354. We've done operation in the last slides. And VA equals to 1.38J. There's a mistake that I made. This is VB relative to A is 0.8 omega ABJ negative. So we've calculated I. We get omega BC equals to 2.26 radian per second. And then on the J parts, we take this part, 0.354, 1.384, and 0.8 omega BJ. So then we rearrange this equation, and we know omega BC equals 2.26. So we calculate omega AB equals to 0.354 times 2.26 minus 1.384 divided by 0.8, and we get the omega AB equals to 0.730 radian per second. That is our solution for the velocity. So we have answered that for the velocity. Yeah, so that's our answer for the velocity. Now we can use the same approach now to solve for the acceleration. So let's write the acceleration equation back. So you have got AB equals to AA plus B relative to A. And do you remember all the equations? So we need to do this by parts. Let's do the simple one. So AB is, because it's rotating about OAB, about C axis, so it's alpha AB cross position vector B relative to C. Yeah, and then minus omega AB square, omega BC square, not omega AB square, BC square, omega BC square. And then position vector B relative to C. Maybe it will be helpful for me to just sketch where the things are. So it looks like this. Yeah. So O, A, B, C. Yeah. So rotating that way. We have all the numbers before us. So we don't know what alpha AB is. So the right thing to do is assume alpha AB as K. No, AB is not, this is BC, alpha BC. Yeah. So alpha BC, and the direction is K, cross position vector B relative to C. We have to import B relative to C. I don't have it with me here now. I'll try to check. And then minus omega BC. We know what omega BC is, 2.26. 2.26 square. Position vector B relative to C. Yeah. So and then you can start again with position. What is AA? You know what AA is? AA is, it is 2 radian per second. Let me, is it 4 radian? 2 radian per second square? 4 radian per second. Yeah. So we know that alpha AB K, and then you have to rewrite position vector. Sorry. So you write, this is position vector A relative to O minus omega AB square. You know omega AB square is already 2.26. This is omega BC. Omega AB is 0.730. So omega AB is 0.730. Sorry. This is omega OA. This position, so sorry. There's a lot of mistakes here. Omega OA square, and then position vector A. So a lot of data to put in. So alpha AB, no, A is alpha OA, sorry, this is alpha OA. Excuse me. This is alpha OA cross position vector. Yeah. So alpha OA is also given. Let me find it. Okay, you have to look for that. So take some time, you try to find the values. And finally, what we have, we already have, let me see, we have AB, assertion B, we have assertion A, and we still need to find assertion B relative to A. So I'm going to write it here. Assertion B relative to A equals to alpha AB K position vector B relative to A, and that's known, 0.8i. So skipping here, and minus omega AB. Also, we know what omega AB is, minus 0.730 square minus 8i. Okay, so that's because it's minus omega square AB position vector B relative to A. So position vector B is minus 0.8, this is 0.73, and you can get the answer. So alpha AB, sorry, 0.8. it's equals to 0.8. K cross I is J alpha ABJ minus 0.7 times 0.8. This is not, still make the same mistake. It's 0.8. 0.8I. So calculated B relative to A. I can box this. I know the whole vector for B relative to A. Have you find what AB and AA is, so that we can combine in the next slide. So I'll put the figures in the next slide. So we have all the data with us now. I have to do it in one go because to save you some time on the screen. So I've got here the position vector of A, which is 0.346i plus 0.2j. Position vector of B is 0.354i plus 0.354j. And position vector B relative to A is 0.8i. And I've compiled all the angular velocity. Omega OA is 4k, omega AB is minus 0.73, omega BC is 2.26, and we know alpha OA is given 2k radian per second square. What we don't know is alpha AB and alpha BC. So we write down all the equations for each point. So acceleration of B, which is this point, equals to alpha BC cross position vector B relative to BC, and then there's another missing here, so it's also, you have to add minus omega BC square position vector B relative to C. So and then alpha A, acceleration AA equals to alpha OB cross position vector A minus omega OA. We need to underline this. So omega OA square position vector A, and then finally the acceleration of B relative to A, same formula, alpha AB cross position vector B relative to A minus omega AB square cross position vector B relative to A. So here I continue with position acceleration of B relative to A is alpha AB K cross 0.8i 0.8i is position vector. Omega AB known is 0.730 square, and then times 0.8i, so you got this for this term 0.8 alpha ABJ minus 2.394. This is point here I. So similarly, I continue with A, and the whole, this is 2k is the alpha OA, and this is omega square 4, and this is the position vector 0.346i plus 0.2j, and I have 5.936i minus 0.2508j. And finally, I calculate for AB equals to alpha BCK cross the position vector minus omega square times 0.354 plus this is the position vector of B relative to C, and I obtain the acceleration of B is 0.354 alpha BCJ minus 0.354 alpha BCI minus 1.808I minus 0.8J. So what we need to do now, after we have all these three boxes, three values of the acceleration A, acceleration B, and acceleration B relative to A, we have to combine that in a long equation in the next slide. So we have the final slides here where I've already taken the I and j part of the equations out, and we have this I part 0.354 alpha BC minus 1.808 equals to minus 5.936 minus 2.394, and you can calculate alpha BC to be 18.42 radian per second square. Similarly, when you take the j parts out, it's 0.354 alpha BC minus 0.8 equals to 0.508 plus 0.8 alpha AB. I might do some mistake during the calculation, so you can do the corrections if you want. But I think as far as I can check on my own, maybe so this is alpha BC. You know the value of alpha BC, substitute into this, and you get alpha AB minus equals to 10.29 radian per second square. It has been a long example. Now one example. And during the examinations, it may take you about 30 minutes, or for those who are fast, it can be done in 20 minutes. So be meticulous, be careful with your calculation. I don't really go for the numbers. I would like to see how you solve the problems, how you approach the problems. But this is what we have covered so far in these 4 bar linkages. And you can see all the examples before this. I think this is the most straightforward way of trying to solve 4 bar linkages. I hope you have benefited from this lecture. Take some time to review slowly. If you don't understand it, review it again. And let me know if you have some problems in the WhatsApp or in the email. Okay, so take care. I'll see you in the next lecture. Assalamu alaikum.